So I'm Sebastian, and I'm super happy to be giving the last talk at today's symposium. And I'm going to be talking about current and future trends in distributed systems. And in particular, I'm going to be focusing on new paradigms that I think will become very relevant in the coming years. But let me start with some of the more established settings. So as we all know, public clouds are one of the most transformative shifts in computing in the last decade, with a large number of companies and developers that are outsourcing their computations to these well-provisioned providers. And in return, they get, quote unquote, unlimited resources. They get a lot of security. They get monitoring systems and sort of all the flexibility and manageability of the cloud. So they don't have to worry about these things. And so it's no surprise that public clouds have become so prevalent today and their use has become so prevalent today. But of course, centralizing or concentrating all the data in just a handful of data centers across the world is not ideal, which is one of the reasons why we have content distribution networks that ensure that data such as movies and pictures and songs and news articles are geographically stored near users. And not only does this improve response time so that when you actually want to watch a movie, you can get access to this movie more quickly, it also reduces network congestion. Now, for a while, developers were pretty happy with public clouds and just managing the resources in the cloud. But more recently, they're finding that managing virtual machines and servers and large complex applications is not as easy as one might want. So now with the advent of serverless computing, developers only need to worry about writing the logic of their applications, and they don't need to worry about any of the other jobs that they'd had to do before. For example, provisioning resources or load balancing requests across their virtual machines or orchestrating jobs across their virtual machines. All of this is taken care of by providers, which is fantastic for developers who don't want to deal with this complexities. Now, going forward, just like we had content distribution networks that help us bring data closer to users, we now have cloudlets or edge computing services that let us bring computation closer to the users. And again, the idea is the same. Instead of having a request go all the way to a data center that could in principle be on the other side of the country, now we're going to have these mini clouds that are attached to cellular base stations or Wi-Fi base stations, and that are all over the place, so they're much easier to reach. Now, so far, all of the technologies that I've discussed are deployed by services like Amazon and Cloudflare and Microsoft, right? Big companies. But in a completely parallel universe, there's also this strong movement towards decentralization. So the idea in this movement is, forget about providers. Let's just have all users store the data and perform the computation, and then use what are known as consensus protocols to make sure that we all agree on what the state of the system should be. So this is a very different shift in mentality and in infrastructure that has led to an incredible amount of innovation and interest. Nevertheless, all of the technologies that I'm showing here on the screen are already somewhat well known. So instead, what I want to do is talk a little bit about two major trends that I think will become more relevant in the coming years. And these include resource disaggregation and serverless cloudlets. So let me talk about disaggregation first. So if we look at a traditional data center, it's going to consist mostly of a bunch of racks. Each of these racks are going to have servers, typically known as blades. And if we look at each of these servers, it's going to, inside the server, is going to look something like this. It's going to have a motherboard. Admittedly, this is the motherboard of a desktop computer, but a server computer is going to have something similar. And in this motherboard, we're going to have a bunch of CPUs. We're going to have a bunch of memory. We're going to have GPUs. We're going to have storage, network cards, and so on. In contrast, when we disaggregate the systems, what we're doing is we're essentially taking resources away and splitting them up and connecting them with a very fast network, which I'm showing in this diagram here. And nowadays, this is actually fairly common for some resources. For example, storage has been disaggregated for quite some time. So if you're in a data center and your application needs to access storage, often that application ends up reaching the storage through a network. And the same is happening with accelerators such as GPUs and tensor processing units. Now, in disaggregated data centers, we're thinking that this is going to be even more aggressive when it comes to disaggregation. And we're not only going to disaggregate storage and accelerators, we're going to disaggregate even very tightly coupled resources, such as memory. So now you can imagine this scenario where we have our memory, the bulk of our memory, sitting in a memory pool, and our servers are going to have a lot of CPUs. So these are going to be very high density servers with just a little bit of local memory. And the purpose of this local memory is to host the operating system, because we still need someone to actually manage the resources in our data center, and to serve as a little cache so that we can access information for the current job that we're performing more quickly. Now, you might look at this and say, wow, accessing memory that's off chip is going to take a very long time. And this is actually true, but surprisingly, these networks are very fast. So just to give you an example, these networks, these InfiniBand networks that people are using nowadays, can handle up to 200 gigabits per second of bandwidth, and with access latencies of about 500 nanoseconds. And just to give you a comparison, this is about 1 order of magnitude slower than accessing memory locally. So yes, they're slow, but they're perhaps a little bit less slow than people might think. So this is why this is not completely ridiculous to think that we can do this type of extreme disaggregation. Now, at this point, you might be wondering, why are we separating the CPU from the memory? Isn't that the opposite of the whole movement of let's move the compute closer to the data that we've been seeking for the past decade or a few decades, actually? And the answer is yes, but disaggregated data centers bring with them many benefits to cloud providers. For example, one of those benefits is independence. If a new memory technology happens to come out, the operator can just replace the memory blades, this memory pool that I'm showing here at the top, without having to touch the motherboards of the CPU nodes or the storage nodes or the GPU nodes, right? So each of these resources can evolve independently. They can also scale independently. So if a cloud provider is getting a lot of requests from its customers and turns out it needs more memory, it just adds more memory. It doesn't need to add a new motherboard with all resources that come with it, such as CPUs, memory, storage, and all that. So this allows the provider to focus only on the resources that are being demanded. Another thing that's super interesting about this disaggregation is that failures can happen separately. So we can actually be in a situation in which one of our CPUs fail, but the memory is still intact. It's still totally okay. And in fact, some of the work that we've been doing at Penn is figure out how to exploit such failure independence. And one possible idea is to essentially sort of relegate the job or assign the memory of the failed CPU to a brand new CPU that can take over and continue executing. Now, in addition to independence, there's another benefit of disaggregation, which is flexible provisioning. So here, if today you go to a cloud provider, let's say Amazon, and you tell them, hey, I would like a virtual machine that has 3 CPUs, 117 gigabytes of RAM, and 2 GPUs, this is a very annoying request for the cloud provider, because likely they're going to have to give you a big server that contains many more than 3 CPUs. And some of those CPUs are essentially going to go to waste. Whereas with resource disaggregation, the provider only will assign you exactly what you ask for, which is going to improve resource utilization and reduce the waste. Okay, so these are the benefits for why disaggregation has a lot of potential, particularly for operators. But then there's the other side, which is, what about application developers? Are they happy with resource disaggregation? And so one question we can ask is, can one run regular applications or existing applications on these disaggregated data centers? And the answer is yes. We now have operating systems such as Lego OS that can run completely unmodified Linux applications on disaggregated data centers. So this is fantastic. The drawback is, should one run regular applications on DDCs? And in this case, perhaps not. This is a bad idea. And let me tell you why this is a bad idea. The reason is that applications that are not designed for this architecture are going to end up doing silly things, such as the following. So suppose we have two applications, application 1 and application 2. And the goal is for application 1 to send data to application 2. So what it will do is first is going to fetch that data from its remote memory. So here we're assuming it doesn't have it cached. So it needs to fetch it from remote memory. That's one round trip. Then it needs to send it to application 2 over the network. And then application 2, let's say it doesn't need this data right away, or maybe the data is too big to fit in the cache. So we're going to have to then send the data back to the remote memory. And so if you notice, we move data all over the place, but the final result ended up in the same place. So it's a little bit silly, which is one of the reasons why, if you want to develop applications that are efficient in disaggregated data centers, maybe those applications need to actually know a little bit of the infrastructure, which brings us to a couple of open questions for which we don't actually know the answer at this moment, which is, should disaggregation be transparent to applications? In other words, should the application be aware that it is running on a disaggregated data center, or can the application be completely agnostic and maybe we can provide some kind of layer that takes care of addressing issues like the one I showed in the previous slide? Another question is, what kinds of applications are a good fit for this regime? What about big data applications like the kinds that we run on Spark and MapReduce? Are those good fits for this kind of architecture? Finally, how do we implement resource sharing and virtualization? So if we want to run multiple tenants on this architecture, how should we enforce that? Should each resource have its own manager that enforces isolation across different users? Or should isolation be enforced by the network itself, since everything is going through the network? So these are questions that we're still sort of looking into to try to get a better understanding of what the future is going to look like. So disaggregation is super exciting. And another area that doesn't quite exist today, but I think that will happen in the coming years, is serverless cloudlets. So first, let me talk a little bit about cloudlets and edge computing in general. So cloudlets are essentially these mini data centers that are attached to cellular base stations. Okay, so like 5G base stations. And their goal is that when you issue a request, when an application, like for example, this smart glasses, issue a request for identifying an object, normally this request might have to end up going all the way to a data center, and that data center could be on the other side of the country. So that request is going to take a long time. Whereas with a cloudlet, that request can be processed right there at the cell tower, and you can get that response very quickly. Okay, so this is going to improve the responsiveness of applications. And the same is true of things like language translation or trying to get traffic statistics for the nearby area. So all of these are excellent applications for cloudlets. Now, serverless is a paradigm that's becoming very popular today. And it works roughly as follows. I'm going to give you a 1-minute crash course on it. So the idea is that we have a developer, and that developer writes an application in a high-level language, like for example, Python, and uploads that application to the cloud. And the way this works is basically you go to the cloud provider's website, you press upload file, you upload the file, you're done. That's all the developer needs to do. In return, the developer gets this identifier that it can provide to the clients that need to trigger this or invoke this function. Now later, when a client invokes the function, it essentially connects to the cloud provider, typically via HTTP. And this is going to cause the cloud provider to then send this request to a worker that's capable of running this function, that has the corresponding runtime and dependencies and everything it needs to run the function that was provided by the developer earlier. And if no such worker is available at the moment, the cloud provider will just start a new worker that's capable of doing that. So this is fantastic for developers because they don't need to worry about resource provisioning or load balancing or orchestration or any of that. All of this is taken care of by the cloud provider itself. Now with cloudlets, what I'm thinking will happen is we're going to take this abstraction of serverless functions and we're going to allow developers to tell the cloud provider, hey, I would love if this function could be run nearby the users by essentially outsourcing this function to one of these cloudlets. Because currently, the only people running functions in cloudlets are large companies. So you should think of it as Apple and Amazon and Google, who actually rent this very limited amount of hardware that's attached to these base stations. So with serverless cloudlets, this would be a way to democratize access to these fantastic resources by essentially pushing some of these functions to the edge. Now, of course, there's a bunch of questions that remain open. For example, what functions should one run in the cloud versus the cloudlet? Certainly, if the function takes a very, very, very long time to execute, that's not a good fit for a cloudlet. And the reason is that in that case, network latency, which is what's being masked by the cloudlet, is not going to be your dominant cost. And so you might as well just go all the way to the cloud. How to deal with stateful functions, functions that actually need state, because if they need the latest state, they might end up having to go to the backing data center, the backing cloud all the time. So in that case, those functions will probably not benefit from running in a cloudlet. So we probably need to build functions that can survive some level of inconsistency or just require things like eventual consistency. Finally, unlike data centers where we have many racks of servers, in cloudlets, we have a handful of racks of servers. And so now we have this question of how can we share this super resource constrained infrastructure across many users who want to use this infrastructure. So this is going to create a ton of super interesting optimization and scheduling questions that I think will be very interesting in the coming years. So just to conclude, I'm super excited about all of the progress that has happened in the past few decades in the area of distributed systems. We have things from data centers that have taken over the world to decentralized and blockchain systems that are becoming, our giant sources of innovation. We have content distribution networks and edge computing where we can get data and functions closer to people. And then we have this idea of disaggregation where we can do a better job allocating resources and scaling those resources.